So we're going to talk about bio. Does everybody have the packets? They're on by your teacher's computer up here if you didn't grab them. And again, I understand this is your first day to do an APES session like this. The packets are just great information for you to have. I mean, it parallels the notes a lot. There's a lot of extra information if you're a reader, which is almost like I've never met a high school student that was a reader. And this is not you. I'm judging by all the high school students that I know. Because I can give them instructions that are like 3 steps of written, and they don't read all 3 of them, and then ask me 15 questions because they didn't read the instructions. So that's how I know you're not readers. I assume that somewhere when you see like 10 or 15 words written in a row, you start being like, all right, that's it, I'm out. I'm done, right? I got to 10, and I was with you, and I got to like 11 and 12, and I can't read that much. Okay, but anyways, there's lots of good information there. The one-pager is like an outline of mostly what we're going to talk about. So you can see lots of blanks in there that you can fill in, and we can talk about. If you want to hold me accountable, and I either didn't describe something at all or didn't describe it well enough, and you want to say more about it, then you want me to say more about it, then please bring that up too. That's totally fine. So biogeography, right? I like to say things in the simplest possible language, and I say a lot of these things. I said it to the last group, and I'll say it to every other group that comes through here. I'm going to ask you about a lot of big concepts in environmental science. And so I'm going to ask you if you understand this thing. And you're going to do what all high school students do. You're going to be like, yeah, you're doing good, right? And then I'm going to say, could you explain this concept to my 3rd grade son, Quinn, who is a real person? And so you should be able to explain it to Quinn well enough that he could explain it to his friend. I'm just telling you. If you can't do that, you don't understand it. I'm just telling you. Right? I'm just being real with you, right? Because I don't have to see you tomorrow. You don't have to like me ever. I'm just telling you exactly like it is. So if you can do that, you understand. That's not about environmental science. That's not even about science. I teach physics and engineering as well. So I would say any science topic and most math subjects, and I don't know English or social studies or something like that, but math is for almost everything, right? If you can't explain it to a 3rd grader, you don't really understand it. You might know some buzzwords. You might be able to answer a multiple choice question, but you can't answer an FRQ question necessarily. Have you taken FRQ questions in your APES class?
Yes.
So you know kind of what the format and what they're like, right? Every Friday?
Every Friday.
Okay, nice. Okay, good. So, so you've seen them and you know what I mean. So those explanations, this sounds funny to say, but AP Environmental Science, and like I apologize, I'm telling you too much stuff off topic. You can just, you can even these. Do you know what that means? Cut it out. Yeah, cut it out. Okay, okay. I just realized like I'm way old, so I realized I start referencing things that like these guys are gonna get, and then like you might be like,
what is he doing?
I've never seen that vine before. My 13-year-old keeps asking me about vines. He's like, have you seen this vine? Have you seen that vine? And I'm like, dude, I don't like spend endless hours on the internet looking at nonsense. And so he's like, man, see, he played this game when he came with me. We drove here and he stayed with me last night so he could come eat Cajun seafood. And he's in the hotel right now. And the whole time he kept trying to find a vine that I've seen. And I kept being like, I don't know the last time I watched a vine. But he kept being like, oh, surely you've seen the one with the something. And I was like, so I disappointed him. But if you can't, most of these APES FRQ questions are like, describe two causes of blah, 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 right? And your answer would be just what I would say to my son Quinn if I was trying to describe it to him. Right? And I do this because I want to have hippie environmentalist kids. Right? So I literally do this to Quinn when I go home. Okay? Am I making sense? Yes. Right? So biogeography, I say it in the simplest possible way. I say biogeography is like the study of what lives where and why. Right? So we don't just find any old animal or any old plant where it goes. We find them there for particular reasons. And you could be really sophisticated about this. And there are PhD people that study a particular family of a particular insect. I was listening to a podcast about a woman that studies ants. Right? There are something like 50 species of ant that we've studied, like the human beings have studied, and there are 14,000 different types of ants. So you could spend your entire life studying one particular type of ant if you wanted to. But AP Environmental Science is not that kind of class, right? I'm trying to, in a small way for one Saturday morning, I want you to be like good environmental citizens that understand the big picture, which means you understand the 3rd grade explanation of a whole lot of different concepts, so you could then understand them. If you want to go learn a lot more, go study this in college. Go take a whole semester-long course about a particular subject and become experts in it. But that's not what we're really trying to do today, or really in environmental science. So we're going to talk about this in terms, and this, I apologize, this is not my PowerPoint, this is Nindy's PowerPoint, but it's a little bit jumpy, like it kind of seems to like go a little bit all over the place. I kind of feel like that, so you're probably going to feel like that. But these are some of the three big patterns, right? Latitude tells us what lives where. How does latitude tell us what lives where?
Like on the globe and all.
So different biomes tend to be spread out by latitude, and it's not a perfect thing. This is a big pattern, and there's patterns within patterns within patterns, right? And we're going to talk about some of those different patterns. So latitude says if you are at the equator or near the equator, then you probably better be adapted for hot temperatures, constant hot temperatures, right? And as we go, I'm just going to talk about the northern hemisphere. It's kind of selective, but I've never been to the southern hemisphere, and most of the human beings on the planet are in the northern hemisphere. And so as we go to the northern hemisphere, as you go further and further north, we expect that it gets colder and colder and colder. So you better be adapted to colder climates. If you're in the temperate part, like in the middle, like the more north than us right now, but middle northern U.S., you better be adapted to hot summers and cold winters because you have big temperature changes. And then as you get up into Canada and those types of places, you better adapted to cold all the time, right? And so you better have some sort of mechanism to either hibernate or burrow so you can get away from the cold or migrate away from the cold or something. Is this making sense, right? So you can start to figure out what lives where based on those. And we're not going to go into those adaptations in this presentation, really. There's other ones that do that. Another thing we have to talk about is weather versus climate, right? Weather versus climate. Do you know the difference between weather and climate? So weather, that's a very good way to say it, I think. Weather is temporary and climate is over time. Really, climate is an average over big periods of time. So the weather, whenever you talk about the weather, you're talking about a very finite amount of time. So I might say, what's the weather going to be like tomorrow? What's the weather going to be like next week? We might just say, I might even just say, oh man, I'm from Houston. And so in Houston, October was really cold. It was colder than I expected. But it's a finite period of time where I'm going to describe. And what I'm typically describing is one or more of these things, right, when you talk about the weather. Does that seem fair?
Yes.
Right? We talk one or more of these characteristics. When we talk about climate, I'm going to skip a slide here. When we talk about climate, we are talking about averages of a region, so not necessarily one particular place, but a bigger area, and we're talking about at least a 30-year average. And so often this can be more than this. This could be averages of centuries. If we're looking at climate data that goes back, hundreds of thousands of years, so this could be centuries of averages. And when we talk about climate, we're really only talking about two things. We're talking about temperature and we're talking about precipitation. Those are the two big things. We're not talking about like the average cloud cover in an area necessarily because we don't have good ways to measure that. And that's mostly why, is because we don't have good ways to measure anything but temperature and precipitation very far back. We've only been measuring temperature and precipitation as a human species for like, in different places, but like 100 years maybe, right? I think it's less than 100, right? Yeah, 70, 80 years, something like that. So we don't even have a century's worth of actual hard data. Everything else we're doing is called proxy data, where you measure one thing, and that helps you deduce what the other thing is, and we don't really need to get into that. Also, these are two good ways to decide what lives where, right? There's another NIMSY presentation, I think it's one of the ones you're getting today, on aquatic biomes, and so you just did that, right? So you looked at the bell curve of the zone of tolerance, right? And so for these things, all these species have a zone of tolerance that they can handle. And how much precipitation, obviously how much water, right? Are they adapted to be on a really low tolerance of water? And it's not like it's just more water is better, right? If you don't know this. So it's not like you can just say, oh, well, this dry climate doesn't have very much water, but if they get a whole bunch of water one year, that's going to be A-okay. It's not going to be A-okay, right? It's probably going to flood them out. Plants drown just like animals drown, right? And that can be a real problem. In Houston, Texas, they call our soil gumbo clay, right? Because if you take a shovel, is it similar here? Okay, so it's similar here, right? So again, I'm digressing, but it's fun. So like if I go out anywhere in a field and I stick a shovel in and I just start shoveling, I can go about 4 to 6 inches deep before I just hit this clay layer that is massively difficult and painful to dig through. And I don't know if you're like me, if you watch the television show, like, you ever watch Supernatural?
Yeah.
They're always digging graves, right? Or digging graves up in Supernatural, right? And so graves are 6 feet deep, right? 6 feet is how or at least 6 feet. You're supposed to put a grave 6 feet deep. So if I was to go dig 6 feet deep to dig a human-sized grave in Houston, Texas, it would take me a month to do that with a shovel. the clay. Like I'm getting like this much clay out in a shovelful, and it's like taking all of my, you know what I'm saying? And they're out there just like shoveling and doing, do you get what I'm saying? They're out there for 30 minutes and they dig up a grave or whatever. And so, but there are parts of the country, you go to Iowa and you go to Nebraska, where they have black topsoil that is 12 feet thick. And so I've never done this, but you could go to those places and you probably could just be shoveling all day long. It'd be just like, it wouldn't necessarily be easy, it'd be hard work, but you could do it. You get what I'm saying? Right? So, so for us, our plants and stuff have to be adapted to, when we get lots of rain, which we get all the time, then that rain sits on top of that gumbo clay, and it sits up, like, so the water, there's puddles on the ground, which basically means all that ground is flooded, right? It's like a temporary marshland, right? That only lasts for a few days. And if you have a plant that can't stand that, because they would drown, then they're not going to make it. But all of our Texas plants are, if they're native, then they can handle that. Does that make some sense? They're used to periods of extended wet, and they can tolerate that. Because they have their zones of tolerance are adapted to those sorts of things. So now we're going to talk about some of these big concepts that help us figure out some of the big climate patterns on planet Earth. And so the reason for the seasons. Could you describe the reason for the seasons to a third grader?
The tilt of the earth.
So the tilt of the earth. So I'm going to say this. So Quinn walks up and asks me, why do we have 4 seasons? Why is it not the same all the time? And I say, oh, son, it's the tilt of the earth, and I walk away. Is he going to be like, oh, thanks, Dad, that was a great explanation?
The earth tilts like this and it rotates. Therefore, the way the sun hits, it changes, so our seasons change.
Okay, so that's a way better explanation. It's really close, I think, right? So there's a little bit more if you really want to get down to, because just imagine this, like if you take this to heart and you really want to know things you can explain to a third grader, imagine a third grader asking you why, like little kids do, right? And so he goes, why does this happen? And I say, it's a tilt of the earth. Thanks, son, good talk. And he's like, well, why? And then I say, well, it's because the earth goes around and the sun changes the way it hits. And he goes, okay, well, why does that do it? Right? So I would say there's a little bit more. I would say you're really close, but I would say there's a little bit more, right? Do you guys have any more you want to add? Anybody? First of all, I appreciate you offering your answer too. Anybody else have any other things?
It's more concentrated in some areas and some other areas it's more spread out.
Okay, that's the last piece I would have to say, right? So just to make sure you understand what he's saying, if I took a flashlight right now, if I took a flashlight and shined it directly on the whiteboard, can you imagine that there would be a circle of light where all that would be, and I could find a distance where I could get the flashlight beam to match up with that circle. Does that make sense? Mm-hmm. And then if I took that circle, if I took the whiteboard and I tilted the whiteboard like this, can you imagine that on that tilted whiteboard, now that light would be spread out over an oval that would be bigger than the circle. Right. So that's essentially what's happening. The sunlight that comes down is heat. Right? It's an energy source that gets turned into heat, essentially gets absorbed by the planet. There's a lot of other factors that go into it too, but it gets absorbed, and that heat gets absorbed, but if the heat is concentrated in a small area, then there's a lot more heat. If the heat is spread out over a bigger area, then there's less heat. And so that's essentially what's happening. So right here in this picture, you can see all of this area is getting almost perpendicular sunshine, right? And this would all be near the equator that gets almost perpendicular sunshine for the entire year. But here, for us in the northern hemisphere, at this particular location, we're getting a big, obviously the sun's not in big arrow rays like this, but this flashlight beam, if you will, would be spread out over a big oval, so now we're just not getting as much heat per area on the ground of the earth. And then when this earth rotates around to over here, then we're going to be the ones in the northern hemisphere getting this direct sunshine like the southern hemisphere is getting right now. So this would be our summer on this side and their winter. Right? And so now, again, are there more things that my son could ask about why this happens? And why does the planet rotate like this? And I'll be like, well, I'm tired now, son. I'm not tired. I mean, but like I described it well enough. Right? Does that make sense, right? And could you describe that on an FRQ, if this was a question, in 2 to 3 sentences? Yeah. And again, other pro tip for FRQs is the more you write, the less you know. Right? And I've graded FRQs for a couple of years as well. Right? So, and I tell you this because you're trained where do you do most of your writing in school?
English.
In English class. And your English teachers tell you all the time, write more, write more, write more, write more. Correct? Right? More is better. In science class, more is worse. I'm just telling you, if I look at this and I just give you this, let's say this is literally an FRQ, this is part B of an FRQ, why do we have the seasons? And I look at this and I'm like, I know how to describe this. I would do it in 1 to 2 sentences, so I'd expect a student to do it in maybe a little bit more, 2 to 3 sentences, right? And I look and I'm grading like literally hundreds of these every day. And so you're doing this and you're like, 2 to 3 sentences, blank, 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 2 to 3 sentences, blank, blank, blank. Then I get to one, and yours is like 4 paragraphs, like half of a page of this. I look at it automatically, I'm like, this person has no idea what they're talking about. Because there's no reason to write that much to answer this really simple thing. And so if you wrote it, you're doing the classic high school thing that I did when I was in high school too, of, I don't really know the answer, but I know a lot of things that might be the answer, so I'm just going to put them all down on the page and hope that they're right. And so don't do it, right? Don't do it. Just write down what you think you know. Even if you don't know, guess at one thing and write it down in 2 or 3 sentences and just leave that thing there. You have a better chance of being successful.
Or restating the stem. You don't have to restate.
You don't have to restate
I always
anything.
tell my students, you don't need to set the scene. You don't need to say it was a cold, dark
There's
night.
no, a galaxy long,
Yeah.
far, far
Livingston
away.
Parish.
Okay. Convection cells. We talked about these in the class. Okay. Could you explain how convection cells impact the climate on planet Earth?
Yes.
Okay, what would you say?
Heat from the sun, then like evaporates and all.
Okay.
All
The
the
heat rises, and then as it cools, it goes back down, and it goes in a circular motion.
Okay, so you're describing why the convection cell happens. All right, so if you can't tell, this is a tilted Earth. This is the equator. This is the Tropic of Cancer and the Tropic of Capricorn. Do you know what the Tropic of Cancer and Capricorn represent?
zodiac sign.
The what?
Zodiac.
They are zodiac signs. Do you know why they're there? I didn't know this till a couple years ago. I'm going to be totally honest with you. I had no idea why they were there. Do you know what they are? When we go back, they're not degrees. I believe they're 23 and a half. Or
Isn't it the angle of the angle of incidence is 90 degrees for each one of them?
at one point in the year, they're the furthest north and furthest south place. So as we go around the Earth, then somewhere is getting direct perpendicular sunshine, right? But where that place is, as the Earth goes around 365 days, it changes where that is. So on this graph, on this picture, the Tropic of Cancer in the northern hemisphere, this is the furthest north place that gets direct sunshine at some point in the year. And they obviously only get it for a very short period of time. This is the furthest southern place that gets direct sunshine in some point of the year. And this is the physical definition of what we call tropics. To be tropical, you have to get direct sunshine at some point in the year. So like, I believe this is 23 and a half degrees north. And Houston, Texas is like 28 or 9 degrees. So they call us, and you guys are a little further north than that. I think you guys are probably 31 or 2, I'm guessing. And but they call Houston, Texas subtropical. And sub is a weird word because sub typically means what? Less or under. But they just mean sub, in this case, as in close to but not quite. Right? So we're tropical almost. And which makes a lot of sense when you spend time in Houston, Texas, because it feels tropical a lot of the time. But it's not quite. We never get direct sunshine in Houston, Texas, so we can't technically be tropical. Okay, that was just a little fun fact. So you're describing the hot air, the hot equator, the sunshine comes down, it warms up the Earth warms up the air, which is really how the air gets warmed up mostly, right? The Earth, down here on the atmosphere where we are, the air mostly gets warmed up by the Earth and the water and stuff, warming it up, and then that air rises, and because of, I'm not going to get into all of the high pressure cells and low pressure cells. It gets to be too complicated. But this moves from high pressure to low pressure area this way. This is about 30 degrees latitude, and then the cycle kind of repeats here. There are 6 cells on planet Earth. They're mirror image right around the equator. So all the southern hemisphere cells are the mirror image. This one I was just describing is called a Hadley cell. It circulates from the equator to about 30 degrees. This one in the middle is called the Ferrel cell, which actually goes from 30 degrees up to 60 and then rotates back around again. And the easiest one to remember is the polar cell because it happens near the pole, between 60 and 60 degrees in the pole. But how this impacts the weather pattern is that this hot, moist air rises as it, this is all near the equator, as it rises, it does what? It cools, and so it can no longer hold its moisture, and that means it drops its moisture, and so we get equatorial bands of hot, wet areas that are perfect for tropical rainforest. Right? So this is why this pattern happens, because it's not just the heat, it's also the moisture, and the heat causes, the sunshine pattern causes these convection cells that contribute to lots and lots of rain here pretty much all year round. Right? And then, by the time we get, the air has been pushed up to 30-ish degrees, and it starts to fall back down again, then now it has no moisture in it. So at 30 degrees north latitude and 30 degrees south latitude, we tend to get most of the world's deserts. And again, this is not an exact rule. You can go find something that's very not deserty, because again, Houston, Texas is right around 29, 30 degrees, and it's not desert. But we're also on a warm body of water coast, which changes things, right? So this is one big pattern, but there's a pattern within a pattern within a pattern. Does this make sense? If you go look at the map, you'll see most of the big deserts are near 30 degrees north or south latitude, right? And so we do some of this in my class. Then, so this is going to be hot and wet, and then we're going to get cooler and drier, and then again, because of these patterns, this ends up being a wetter band again here up here at 60 degrees. It's obviously really cold, but it's going to be a wetter pattern. So this is one of the other big climate patterns on planet Earth. The Coriolis effect. This whole presentation is just full of these big concepts. The Coriolis effect. Do you know what this is?
Yes.
Okay. So do I need to ask you again? Could you describe it to a third grader? This one's tricky because you could spend a long time on this, and there's a lot of physics that goes on here, right? But it's essentially, here's the cells, right? This is the northern hemisphere. This is the northern hemisphere, so you can see here's the Hadley cell, here's the Farrell cell doing this, and they don't really show the polar cell quite so much, right? But the polar cell is up here. So what you would think based on those cells is that between 30 degrees and the equator, we get a predominant wind pattern that's south because of this convection cell, but we get what's called the trade winds that blow kind of towards the equator and they bend towards the west, right? And they're called trade winds because when human trade was primarily sailboats, then this is what powered most of the trade, was this wind pattern near the equator. It's how most of the trade happened. And you would expect in the 30 to 60 degree range, which you can see right here, is northern Mexico all the way up to halfway through Canada. You'd expect the pattern here to be pretty much a north wind, but instead of a north wind, we get a north but also eastward wind that's called a westerly because winds are named by where they come from, not where they go. So these winds all come out of the west and blow this kind of curvy pattern. And again, winds change a lot, so this is a big pattern, and there's lots of tiny patterns within this. And so the Coriolis effect is a description of why we don't get the straight south and straight north winds, and it has to do with the Earth turning underneath the atmosphere, essentially. And this gets into like centripetal motion and physics, and like to give you a real precise explanation would be a lot, and you're not going to get it right now anyways. But what's happening here is the Earth is turning underneath the atmosphere, and as it does that, it essentially makes the winds look like they're bending to us. I mean, that's probably as much as you need. It also has to do with the fact that at or near the equator, the Earth is really fat, and as you get closer to the poles, the Earth has a much smaller radius. When you think about this rotational radius as the Earth is spinning, like a person standing on the Earth would travel in a much smaller circle here than they would on the equator. And it has to do with that as well. But that's the Coriolis effect, and again, it contributes to these major wind patterns. And the wind patterns affect how we pick up moisture out of the ocean, whether you're coming, whether it's an ocean breeze or a coastal breeze. It affects a lot of other things. We'll look at wind a little bit more on a couple other things. The Gulf Stream is one of the major ocean currents, and this is another one of those concepts. I don't spend a lot of time on my class on this. We talk about ocean currents a little bit, but we talk about it as a larger piece where we draw maps and look at what types of biomes exist where on the Earth. We actually do this activity where my kids have to draw a fictional island, and they have to decide what biomes would be on their island based on its latitude, based on its elevation, based on the ocean currents near it, and things like that. Ocean currents, in the simplistic third grade explanation, so ocean currents do two things, or they influence two things. The biggest one is you notice these warm water currents, like I believe the Gulf Stream is. These warm water currents, you see them. They're moving from the equator towards one of the poles. They're carrying the heat away from the poles. And you see the cold water currents, and again, you can just Google this and get 10 different images in a few seconds. The cold water currents are going from the poles back to the equator. It's almost like the ocean currents are trying to balance out the temperature difference between the equator and the poles. And to a large extent, they're doing that. The temperature difference would be much greater if they weren't doing that. Obviously, the temperature difference is still big, right? But we are very thankful that they do it. But if you look at things, there's some really interesting stuff. We talked about how latitude tells you, oh, this must be the tropic right here, huh?
Yeah.
So we talked about how latitude tells you a lot about, what the temperature is going to be like. But it's really interesting if you look at, there's an example that I saw in a textbook one time that talks about Savannah, Georgia, that's like over here, and San Diego, California, that's over here, and they're roughly the same latitude. Have you used this example before?
Yeah, like if you go, anybody ever been swimming in the Atlantic Ocean off of Florida? How warm is the water? You guys ever been to California,
Yeah.
LA?
The water's freezing.
Yeah, or seen pictures of people surfing in California? What is every single one of them wearing?
Wetsuit.
A wetsuit. Because even off the coast of California, where's the current coming from because of the Coriolis effect? It's coming from down
It's coming
Alaska.
There's one called the California current coming down that's a bright blue
Yeah,
current.
the water temperature off the coast of California is really only 70, I think it's 73 or 74 degrees. And if you've ever been in 73 or 74 degree water, it's cold.
Freezing.
Versus what's off the coast of Florida is like bathwater. It's 80, 82, 81.
It's really similar to the Gulf.
Right.
It's really similar. I mean, so I use the example like, so Savannah, Georgia has a weather pattern a lot like Gulf Coast, Louisiana, Texas, whatever, right? Hot, humid type of weather all the time, right? You guys are a little further inland, but I'm like, my house, I actually live south of Houston, so if you know Texas at all, I'm like halfway between Houston and Galveston. Galveston I'm like 30 minutes away from, but I could be at the water in like 5 miles. So I'm super coastal, and so it's hot and humid all year round. Same latitude, you go out to San Diego, California, and it's mid-70s, low 80s all year round. It's never rains. It's super dry, and a lot of that is because this is a warm current going by this coast, a warm current and a warm ocean, and warm water evaporates easily, so you have a lot of water in the atmosphere, and you have a cold current going down this side. This is not the only factor, but this is a large factor. And so that's what I'm saying. When you start to put these patterns on top of each other, you start to see lots of really interesting things. Okay, have you talked about El Nino Southern Oscillation, ENSO? Okay, so I saw a couple heads shake, but I heard some no's. Okay, so we're going to talk about this. So this is 2 different pictures, and first I have to tell you what you're looking at, right? This is North America, Central America, South America. This is the western coast of those continents and countries. And then this is Australia, Indonesia, and then what's not pictured up here would be the coast of China and India even, right? So it's primarily we're talking about the Pacific Ocean and the coasts of those continents that borders the Pacific Ocean. It's really where El Nino happens. And so this is a normal situation for what's going on here. There is normally this strong westerly that we talked about. They're showing this wind blowing this way, and it physically blows the top layers of the water, which are the warmer ones pictured by the red, orange, yellow. It physically blows this warmer water towards Australia and Asia. Like if you could measure the water level would physically be higher over here because the wind has blown so much water over there, right? And so it's the top level of the water. And all these big bodies of water, again, this is a complicated subject to get into in a session like today, but we'll talk about it quickly, has something called a thermocline. A thermocline, and big lakes have it, the ocean has it. It's basically a dividing line where the water gets much colder. And across the thermoline, the water doesn't mix very much, almost not at all, right? So I'm not saying that if you're in this water, it gets cooler as you go down. But when you cross the thermocline, it gets dramatically cooler. It's just not a linear type of graph anymore, right? So anyways, it separates the 2 layers of water. That's the most important thing you need to know about it. When you push this top warm water off of it, it's kind of like you took the lid off the container. So this thermocline is no longer flat like you might expect in a body of water. It's like this. This is actually really important because in aquatic ecosystems, did you talk about aquatic ecosystems in your last one? Did you talk about fall turnover and spring turnover in lakes?
No.
Right? So again, in a lake you have a thermocline. In a body of water you have a thermocline, and what this does is it keeps these organisms up here mostly and these organisms down here mostly. In an aquatic ecosystem, again, I'm doing this super simple, so forgive me if you know a lot more about this than I do. Here, you have no problem having oxygen when you live near the surface because you're near the air, so you can get plenty of oxygen in the water all the time. But you have a problem not having nutrients in the water, and without nutrients in the water, you can't have phytoplankton in the water, and phytoplankton are on the bottom of the food pyramid because they're little microscopic plants that are going everywhere, right? Down here, you have tons of nutrients because you've got all of the bottom of the ocean, so there's plenty of nutrients. but there's not enough oxygen. So in a lake, you tend to, twice a year in the fall and the spring, you tend to have a turnover where the whole lake kind of flips upside down. So the bottom comes up and brings its nutrients, and the top goes down, bringing the oxygen down to the bottom, and it kind of keeps things in check a little bit. This thermocline being like this in a normal situation makes South American coastal waters some of the richest fisheries in the world, right? More like small fish from what I understand, sardines and mackerel and those sorts of things. This is where like the bulk of it worldwide comes from. And it's because of this weather pattern. And this is all the normal situation. Okay, so that's normal. El Nino, right? The simplest answer to what causes an El Nino is a reversal of this wind pattern. You can see them showing the wind. It is no longer this traditional westerly. It is blowing in the other direction. And technically it doesn't have to blow in the other direction. Sometimes an El Nino can happen just because the winds die down to like almost zero. So the wind either goes away or actually blows in the other direction. So that does a lot of things. When you look at like a list of effects of El Nino, it does a lot of things. But one of them is that now you can see this warm water is spread pretty evenly between these two continents, across the Pacific Ocean. That means a thermocline isn't happening, which means this fishery on the South American coast suffers big time, right? It's really bad. An El Nino pattern is typically about a year. It's like 9 months to a year on average. 9 to 10, I don't know the exact. 9 months to a year is good enough. So the other big effect, other than these fisheries being not productive, is that any of these coastal places, including coastal North America, including, especially like California type of coast, any place that was really dry, so like the coast of California, again, I've mentioned this a couple times, especially Southern California, not Northern California so much, is really, really dry. They don't get a lot of rain. Almost all their water comes from rivers that start in Colorado or something like that, and so that's where all their drinking water and stuff comes from, because they get so little precipitation. In an El Nino year, California would be super wet. They would get more rain in a year than they typically ever get. Places, I can't talk about specific places that much, but the places that are really wet, like a place like Houston, that typically gets a lot of rain, would be super dry. And there's a complete reversal of the pattern, right? Places that are wet become dry, places that are dry become wet. And not just like a little bit reverse, but like a tremendous reversal. In California, they'll have like mudslides, because they don't have a lot of vegetation in California, because it's kind of scrub brushy, because they don't have enough water normally to support a lot of vegetation. So when they get a lot of water, the dirt turns to mud, and they have a lot of elevation changes, and you literally can watch houses sliding down the side of a mountain in a mudslide, like slow motion, right? It takes them a long time. So, I mean, it's a really interesting phenomenon, but it's also a disaster, right? It's a disaster like for us, like hurricanes and flooding and stuff like that, right? So that's what an El Nino does, and it's a complete reversal of the weather patterns. It's the big effect that affects human beings. The wet places become dry, and the dry places become wet. And I can't reference a lot of specific places that much. There is a third option that's not on this slide. I don't have a picture of it anywhere. And it's called La Nina, right? El Nino is a complete reversal of the wind pattern that causes a complete reversal of the ocean temperature pattern and the weather pattern. La Nina is this wind, the normal wind, the westerly. It blows even harder than normal, and it causes the weather pattern to be the same as it normally is, but stronger. So the normally wet places become wetter, and the normally dry places have droughts. Does that make sense how that's different than El Nino? Right? So that's El Nino and La Nina. And then another big concept we're supposed to talk about is the greenhouse effect. And I was trying to open something up. I'm going to try one more time and see if I can get this to work. Sorry, I'm hoping this will work, because this is really useful. Oh my God. It's just going to be the same thing. I can't get it to work. Okay. So back to the presentation. So do you know what the greenhouse effect is?
Trapping carbon dioxide.
Is it trapping carbon dioxide in the atmosphere?
It's the warming of the earth.
It's the trap. Heat gets trapped.
When the sun rays come down, the heat and that can't leave the atmosphere. So it's like a greenhouse. When the sun comes in, the heat stays there, and it just gradually gets hotter and hotter.
Okay. Okay, so there's a lot of correct things that you said. I wouldn't say that any of you said it correctly. If that makes sense. A lot of the pieces that you said were correct. You're on the right path, right? So first off, right, when we talk about the greenhouse effect, right, this is something that you experience many, many times, right? Every time, imagine it's a May school day, right? Just so you understand, this is a real thing. It's not something somebody made up. This is also not a scientific theory that somebody's debating, right? There's no controversy about the greenhouse effect. It's a very real thing. Life on this planet depends on it. It's happening, right? The climate change debate, you've heard that terminology, right? The climate change debate, right? It's not about the greenhouse effect. It's a real thing, right? These days, there's not even really very much debate about whether the climate is changing. Most people have accepted that the climate is changing. We've measured that the climate is changing and temperatures are changing. So there's not a ton of debate about that. The real debate amongst politicians or other people in bigger culture is about, are human beings causing it? Right? That's really what there is a debate about. So the greenhouse effect, it's a May school day, right? It's a sunny May school day, and you either drive your car or ride with a friend and park the car, go to school, you finish school at 2:15 or 2:30 or something, right? So you walk back out to your car 15 minutes later, and you open the car door and you expect to get greeted by heat. Like a little bit of heat? Or like you walked into an oven? Like you walked into an oven, right? The same way in Houston, Texas. And so, if you don't understand the greenhouse effect, that should make no sense to you. I understand it makes sense to you because you've lived for 14 or 15 or 16 years on this planet and you've done this a bunch of times, so you know that this happens. But if I was to set this desk right next to your car in the parking lot all day long, right, for those 7 or 8 hours of the school day, and I went out and touched this desk at 2:30, then I'd expect this desk to be warm, right? It got warmed up by the sun, but not like burning hot. Not like I can't touch the seat belts. I can barely touch the steering wheel to drive home because I feel like I got third-degree burns, right? So that doesn't make much sense that they both sat out in the same sunshine, and this one heated up a lot and that one didn't, right? Until you understand. But the heat gets trapped inside the car. And so we do need to go a little bit deeper than that, though. Okay, so that is the first level of understanding, is that yes, we are trapping heat inside of the car, which basically is a greenhouse, right? So, and the greenhouse effect of the atmosphere, we'll come back and expand this to the atmosphere in just a second. But first I want to talk about it with the car example, because I think it makes a lot of sense. And if you get a chance, go look at this PhET simulation on it. It makes a lot of sense too. PhET's really great for a lot of science concepts. But it's like all the doors are locked. It's a high security operation. Okay, thank you. So the reason that it gets trapped in your car specifically, and a greenhouse works the same way, right? And farmers have been doing this for however long to extend their growing season, so that when it was too cool for those crops to keep growing, they can get it for a couple of extra weeks or a couple of extra months. It's also why you don't see nearly as many greenhouses in southern Louisiana and Houston, Texas, because we don't need them very much, because we already have a long growing season, right? Very rarely in Houston, Texas do we need extra heat, right? That's not something we're looking for very often. So in your car, right, the sunlight that comes down is actually 3 different types of light, right? And if you've talked about the electromagnetic spectrum in physics or in chemistry, right? So all the different types of light. So you know that like microwaves are actually a type of light, right? And gamma rays. Do you know why gamma rays are important? Because of the Incredible Hulk, obviously. So there's 3 different types of light that actually come down that we call sunlight. Visible light, right, which obviously what we see. Ultraviolet, we call it UV light. What does UV light do? Gives you a sunburn, right? Tans or burns. And the third part is called infrared light, abbreviated IR a lot of times. So infrared light is the hot part of the sunshine. On a cold day like today, when you stand in the shade and it feels kind of cool, forget the wind. Let's say there's no wind, because wind's another factor. But if there's no wind, you stay in the shade and it feels cool, you step in the sun and it feels warm, it's not like the air was a lot warmer in the sun than it was in the shade. It's the actual heat from the sunshine. That's the infrared part. The visible part's not warm, and the ultraviolet light's not part warm. Infrared is also the part in a heat lamp you see in a fast food place. The little red lamps that they put the food under while they're waiting to run it out to your table or whatever. Those are infrared light. So there's 3 parts. Those parts go through windows pretty well. I don't know what the percentage is. I'll have to look it up, but it's most of it, right? It mostly goes through, some gets reflected. It comes in. When it comes into your car, it hits your dashboard or the steering wheel or the stuff in your car, and it warms that stuff up. It gets absorbed and it warms that stuff up. It does the same thing to the sidewalk, right? Like, I assume there's times when you can't walk barefoot on some of the black sidewalks or black stuff out here, just like you can't, you have to wear flip-flops or something like that just so you don't burn the bottom of your feet. And you can't even go to the beach in Galveston a lot of the time without burning your feet, right? Because the sand is too hot. And so it warms that stuff up. Now, all 3 parts of that sunlight have now turned into infrared light because everything that's hot radiates infrared light. Human beings radiate infrared light all the time. It's why if you like Call of Duty or first-person shooters and you put on your infrared vision, right, it means you're putting on goggles that allow you to see infrared light because our eyes don't see that type of light. And that type of light travels through walls, so you can see warm bodies through walls and stuff as well, because that type of light goes through walls. Visible light obviously doesn't go through walls. It doesn't go through solid matter unless it's water or glass, clear plastic or something. So when it comes back out as infrared, infrared doesn't go through glass very well, right? It's not that all of it stays in there, because if all of it stayed in there, you literally would be burning. I don't actually even know what percentage it is, but let's just make up a number and say 10% of the energy. Sunlight comes in with its heat and its energy, warms up the car, and then if that heat energy just went back out the windows, no big deal, right? It would warm up a little bit, but it would stay the same. But if even 10% of that energy stays in there, then after an hour and 2 hours of storing 10% of the energy that came in for hours and hours and hours, you end up with excessive amounts of heat. Am I making sense? Right? So that's how a greenhouse works. You allow the sunlight to come in, but you don't allow all it to go out, is essentially what works. And you don't have to really even do anything except for put up a clear piece of plastic or glass to let the sunlight in and kind of trap that air molecules inside. So in the atmosphere, we obviously don't have a panel of glass that goes all the way around the Earth. Even though in the FET you can go do that in their little simulation and see how it works. And what you would see is, this is kind of similar to what they're showing here, they use the yellow dots to represent a photon of sunlight coming in. The yellow dots come in and strike the Earth, and then you see a red dot coming out, meaning it's an infrared photon of light now. And red dot comes out. When it comes out and it hits the glass, some of them go through, and some of them get reflected back in. And so you can start to see how this starts to hold the heat in and warm everything up. So obviously we don't have a pane of glass, but it kind of seems like it. It kind of acts like we have a pane of glass. And so what's acting like the glass in our atmosphere?
Moisture.
So generally we call them greenhouse gases, right? You'll see them called GHGs all the time. So what you guys are giving me are examples of greenhouse gases. So one of them, the big one people talk about is CO2, carbon dioxide, right? So that's one of the big ones. You could look at a list that's like 15 long, and there's lots of things on there, right? So CO2 is one of the big ones. And what did you say in the back?
I said moisture.
So is H2O a greenhouse gas? And the answer is absolutely it is. Yes, it is. Nobody ever talks about it in the climate change debate because we're not trying to remove moisture out of the atmosphere because then we've destroyed the whole hydrologic cycle and we got bigger problems than climate change. So it's important to know that it is one, right? We talk about the other big things in the atmosphere. Nitrogen, right, being the most abundant. Nitrogen, is nitrogen a greenhouse gas?
Yes.
No, because we'd have serious problems if it was. Right? Nitrogen is not a greenhouse gas. Oxygen?
Yes.
No. Oxygen, no. I would say the third big one that you should really, really be familiar with, there are other ones you could be familiar with, is methane. It's a really big greenhouse gas.
I always tell them, the bigger the molecule, it's probably going to be a greenhouse
I never even said that. That's a good
I mean, like nitrogen, N2, atmospheric nitrogen, it's a small molecule, made of 2 atoms. O2, oxygen, it's made of 2 atoms. It's not very big. Once you start getting into 3 atoms and bigger, then it could potentially be a greenhouse.
So carbon dioxide and methane are like the 2 big ones. And carbon dioxide because there's so much of it in the atmosphere because every time we burn a fossil fuel, we're releasing it. And methane along with some other chemicals, is actually a worse greenhouse gas than carbon dioxide like on a one molecule, it actually holds more heat in than carbon dioxide does. It's just there's a lot less methane in the atmosphere. So carbon dioxide has a bigger overall effect because there's so much of it. But on the molecule-to-molecule comparison, methane is a worse greenhouse gas. And that brings me to another point about this, is that you can start to have like philosophical conversations about climate change and environment. Like most environmental issues, if you have these kind of conversations in your household, and maybe your parents have very definite opinions about some of this stuff, and maybe they disagree with some of the things that you're going to learn in environmental science or whatever. But these tend to be emotional issues for a lot of people, right? It tends to be really hot button issues. And so we start to ask the question, is the greenhouse effect good or bad? You can have a conversation. Is it good or bad? So,
Pros and cons.
both or neither, right, would be appropriate to say, right? Without the greenhouse effects, we don't live here, right? Nothing on this planet is the way that it is. We need that warmth. So, like, it's kind of like people act like the these greenhouse gases in the atmosphere are a blanket around the earth, kind of keeping us warm, right? And a blanket is good when you're cold, right? 2 blankets is good when you're cold. 10 blankets even when you're cold is not always good, right? So too much of a good thing is not a good thing, right? So it's a balance, like most things in the environment. It's all about having a balance. We can't have no greenhouse effects. So it's not like we're trying to get rid of the greenhouse effects or eliminate the greenhouse effect. We just want to make sure we keep things under control, right? And the rate of change we've seen has been alarming, right? So we're not really supposed to talk about that much, but that's okay. Okay. So there's a couple other pieces here, and again, they're kind of odd, like the Kyoto Protocol. Kyoto Protocol was a big international meeting from all representatives of all the countries of the world to discuss reduction of greenhouse gases to reduce climate change. This was the first big meeting like this. It was in 1997. You can see down here in the bottom left. It was pretty unsuccessful. The U.S. signed the treaty but didn't ratify it. I don't really know what that means politically, but it basically means we didn't care. A lot of countries had a lot of ideas and they proposed like some rules, but there was no real binding agreement. Like it's kind of like if your parents give you a bunch of rules, if your parents give you a curfew, and then you keep coming in late over and over again and they never do anything, do you stop coming in late?
No.
So this is what this agreement was like. It was like a whole bunch of rules with no real consequences for breaking the rules, so nobody really did anything. We've had a lot more climate talks with sometimes more effect. You know, they were in Paris. Paris last year? Mm-hmm. Paris was last fall, about a year ago. The world met in Paris, and it was one of the more successful meetings. 2 or 3 years before that, they met in Copenhagen. That one was, from what I understand, you read these papers and it was mostly a dud, right? Not a lot has happened. But we really haven't taken a lot of meaningful action as a global society on most of this. And one of the big sticking points for this is more cultural stuff, but I think the cultural stuff is fun, is that when you have a group of countries sit down, all the diplomats and representatives from countries sit down as a group together, and what happens is all of the rich countries, so Europe and North America and Japan and China to a growing extent, sit down and say, we got to do something about this. It's affecting our citizens, it's affecting our biodiversity, it's in a lot of places affecting their water supply. China gets a lot of their water from glaciers that are frozen all year long, and those glaciers are going away because of climate change, and if they go away, then China doesn't have enough water for their, these are like big problems for countries. These are like not a joke. And they're like, we gotta do something about this. So they say, all right, let's do something. And then, like the African countries and the Southern Asian countries and some of the South American countries stand up and be like, you can imagine this argument if you were had like in a normal language. They would say, wait a second. So you basically spent the last 70 years dominating us economically, militarily, in every possible way, mostly because you used fossil fuels for the last 70 years. That's the biggest key advantage that all the rich countries have had, is that they've had access to this technology way longer than the other countries have. And you've done all this pollution because we've done little or none of it. And now you're telling us that we can't do that to help our people get electricity and water and grow their food and do all that kind of stuff? Because, you get what I'm saying, right? Like, you can imagine this with like your older brother or sister or something like that, and you'd be like, wait, you screwed all this stuff up and now I gotta help clean it up? And so it's really hard for the world to come to agreements, right? And so I'm not saying who's right or wrong necessarily, but it's very, very difficult to come to agreements that way. And I believe we've probably only got like a minute or two left. Again, I told you it's kind of all over the place. The rain shadow effect is this idea of if you've got a body of water, an ocean, a coastal body of water, you typically have a small mountain range and a larger mountain range called like a coastal range and a cascade range. because we've got an ocean plate. Have you talked about tectonic plates at all in your class? I haven't either in my class. A tectonic, you know what tectonic plates are from 3rd grade science, right? So if you've got two plates that are smashing into each other, and one's an ocean plate, and one is a coastal plate, and they're crashing into each other, then the coastal plate tends to buckle, right? Because the ocean plate is more dense and tends to slip underneath the other one. There's a lot more going on there that we don't need to talk about. So you end up with this type of pattern. If we have a wind pattern that's predominantly from the ocean inland, then
the following students should meet at the Lubbock table to receive their gift card. Lily Hayden, Noah Jeffers, Kylie Milligan, Maria Rushing, Ella Bozard, Bailey Furness, Joe Welch, Hayden Lilly, and Max Brown. We'll now rotate to our next session.
So I'm going to finish this really, really quickly. The rain-shot effect is when this warm air with lots of water in it gets pushed up a mountain, it cools. When it cools, it drops all its rain. So one side of the mountain gets really wet and lush and foresty. The other side of the mountain gets no rain at all and ends up being a desert. And we call that the rain-shot effect. Okay?